afternoon from Zurich. My name is Magdalena Marszałek. In Zurich Instruments, I work in the technical sales, and today I am your host, and I have the pleasure to welcome you all to the webinar focused on photonics applications. From today's webinar, you will learn how to boost your optical signal detection with lock-in amplifiers and Boxcar Averagers. Well, I have introduced myself in the beginning. Now let me say a few words about us, Zurich Instruments. The company was founded in 2008, and since then, we constantly strive to deliver the highest quality signal measurement equipment for researchers all over the world. Today, we will be talking about the use of lock-in amplifiers and Boxcar Averagers. However, we have teams and products dedicated to impedance measurements as well as quantum computing. I can proudly say, as a scientist myself, that we are run by scientists for scientists. In 2022, we have over 100 people working in the offices in Zurich, but also in the USA, China, Germany, South Korea, Japan, and France. Since 1st of July 2021, we are part of the Rode und Schwarz family, but our mission remained the same: to provide best-in-class dynamic signal instruments for advanced research and development labs. Today's presentation will be delivered by Dr. Gustavo Certi. Gustavo has joined us recently. He holds a PhD degree from the University of Zurich, and with his experience in ultrafast and terahertz spectroscopy, he has strengthened our test and measurement team. Speaking of spectroscopy, allow me to mention our two newest members of the lock-in family, SHFLI 8.5 GHz and GHFLI 1.8 GHz, that, with the currently broadest frequency range in the market, are enabling you to move the line between the known and the unknown even further. Contact us to learn more about them. And what will you learn today? Today, Gustavo will share with you good practices on the noise floor reduction and introduce ways of modulation and signal recovery. I'm very much looking forward to his presentation. But we are here for you, and we want to give you the chance to find the answers to the questions that you may have during Gustavo's talk. Our traditional Q&A session will take place right after the presentation, so please make a good use of the Q&A tab below. You can enter your question anytime. We will collect them and answer as many as possible after the talk. All questions, together with the answers, will be gathered in a written form of a blog post and published on our website. You will also get a notification when this and the recording of the video are available. We look forward to your active participation. I hope all is clear. And now, over to Gustavo.
Hello, everyone. Hello, everyone, also from my side as well. I'm very happy to be here today presenting this webinar. Thanks a lot, Magda, for your kind introduction. As Magda already mentioned, I myself, during my research years, I have gathered some experience in some ultrafast and terahertz spectroscopy measurements, and that is why I'm here today responsible at Zurich Instruments for the optics and photonics applications. In today's talk, we're going to take a deep dive into how to boost your optical signal detection with two of the pillars of our instruments, lock-in amplifiers and Boxcar Averagers. I would like to start by motivating why optical signal detection and recovery is important for optical experiments. Well, in a way, the reason is quite simple. Optical measurements can unlock extremely high measurement precisions. To express this better, I would like to show you here two examples. On the left-hand side, we have the very famous LIGO experiments, where gravitational waves were measured via an interferometric measurements. Thanks to a very extremely high precision, they were able to achieve measure length changes down to 10 to the minus 21 meters. On the right-hand side, we have here the plot of an attosecond pulse, where basically, the time resolution of experiments was pushed down to the attosecond, so 100 of attosecond levels. 10 to the minus 17 seconds. The challenge in these experiments is always to preserve the information content after the signal has been measured and converted into the electronic domain. And that is here where us at Zurich Instruments come into the game. Our mission is to provide the best-in-class instruments, dynamic signal instrumentation, for advanced research and development labs. And how do we do that? Well, our approach is to combine off-the-shelf hardware with adequate specifications in terms of speed, sensitivity, noise, with a software interface that allows the user to benefit from efficient workflows, user interface, smooth user interfaces, and compelling APIs. With this approach, we're able to add new features to the instrument over time, thereby increasing also its value. At Zurich Instruments, we have four main pillars: quantum control systems instrumentation, lock-in amplifiers, Boxcar averagers, and impedance analyzers. Today, we're going to focus on lock-in amplifiers and Boxcar averagers. So what kind of questions or answers can you expect from today's talk? We will first understand on a broader level why lock-in amplifiers are beneficial and what is their working principle. Then we will take a look at how certain instrument settings can affect the measurement results. And then we will finally have a look at the Boxcar averaging technique and compare it with the lock-in amplification in order to understand when one technique might be more beneficial than the other. All of this will be backed up by several application examples for the most common optics techniques. In particular, we're going to have a look at some applications of linear spectroscopy and then pump probe based spectroscopies. So what kind of which are the effects that are generally measured in photonics? So here I have brought you here 4 examples. This doesn't need to be exhaustive, of course. We can start, for example, by linear spectroscopy, where absorption or transmission of a certain sample, a certain species, are measured as function of frequency. Then we might have polarization changes that one needs to measure. For example, when there is the need to reconstruct terahertz pulses, terahertz transients. Then we want to maybe measure some induced absorption on transmission by the means, for example, of a pump probe spectroscopy technique, or also we can have some imaging applications where one wants to maybe use, for example, Raman transitions in order to infer chemical information from a sample and maybe also generate an image of such a sample. And what are the typical effect sizes? Nowadays, experiments have become extremely advanced, and therefore is a common requirement to be able to measure relative variations down to 10 to the minus 7 or even 10 to the minus 8. So generally, these small variations can need to be measured. There are 2 main scenarios where these variations need to be measured. First, on top of a large signal background, as depicted here on the top graph. This could be, for example, a typical case of pump probe spectroscopy, where tiny absorption, transmission changes need to be measured on top of large pulses. Or the other scenario is basically the signal is completely buried below the noise floor of our measurement, as for example could be coherent anti-Stokes Raman spectroscopy. Again, the challenge is always to preserve the information content and increase the signal quality. Then what is then this information that the signal have? So we could have that parameter that varies in our experiment leads to a change in the signal for a certain amplitude and for a certain duration. Then we might have a sinusoidal modulation where the amplitude and phase need to be measured. Or, of course, we might have also more complicated scenarios where multiple parameters are varied, like, for example, multiple frequencies or different amplitudes, and all these parameters maybe need also to be measured simultaneously. But so in a typical optical experiment, basically a prototypical optical experiment can be broken down into 4 building blocks. We start with the source. Okay, this can be most commonly nowadays maybe laser beam, but it could also be a LED, lamp, or even sunlight. Then we have the experiment, that is all the part in our setup that is designed and engineered to address the parameter that we are interested in, the signal that we're interested in. Then we have the detector, that is the device that converts the optical signal into electronic signal. And then we have the signal analysis chain. The signal analysis is often an overlooked part of the setup, and what I mean is that it's generally underestimated how much one can gain in terms of signal quality and information content by a proper signal analysis chain. But before measuring any signal from our experiment, we need to first characterize and understand the noise of our system. Here on the right hand side, we have a typical noise frequency spectrum where the different components are highlighted. We have here shaded in gray the 1/f noise, so this noise that increases as the inverse frequency. This kind of noise is present everywhere in nature, and therefore also, for example, in our laser sources or in our detectors. Then we have the white noise, that is basically here shaded light blue, that mainly comes from the shot noise of our detectors. The cause of the shot noise is the fact that photocarriers and electrons are discrete particles, and generally when an experiment is limited by the shot noise, this is the best case scenario. So basically we cannot go past this shot noise limit of our detector. Then we might also have some noise spikes, as for example the radio or mobile, but also the 50 and 60 hertz lines for the sockets in our lab. A common approach to reducing noise is to do averaging, and averaging can be basically compared to low-pass filtering around DC. Now you can see here that if one averages, does low-pass filtering around DC, is doing this operation where the noise is the highest. That is why, in order to shift the signal of interest to a region where the noise is smaller, we need to introduce a modulation in our experiment. Then, after having introduced the modulation, we can measure the signal modulated with lock-in amplifiers or Boxcar averagers. To be a bit more clear and understand better what I mean, here I have an example of a step response that has been measured with different modulation frequencies. You can see that starting from DC, from 0 hertz up to 100 kilohertz, and you can clearly see how the noise in the measurement, so meaning the thickness of this line, reduces, gets smaller as we go up in the modulation, with the modulation frequency. So the most typical, here I've gathered the most typical modulation techniques that typical optical experiments might have, and the type of device that one needs, of course, depend on the frequency, on the modulation frequency itself. So we have for low modulation frequencies up to say tens of kilohertz. It's very commonly used a chopper, so a device that mechanically, physically blocks the beam with its blades, and depending on the beam shape and also beam size, one can achieve different modulation functions, starting from purely sinusoidal down to short duty cycles modulations. Then, if one then needs to address a higher frequency, higher modulation frequencies, one needs to resort to devices like acoustic modulators or electro-optic modulators. And this way, one can easily achieve modulation frequencies up to tens of gigahertz, and as well here with different modulation functions. Of course, also the pulsed laser themselves can be used sort of as a modulation frequency, and this is typical, for example, with mod lock lasers that nowadays can achieve repetition rates up to like gigahertz in the gigahertz range. Then once we have chosen our modulation technique, we need also to choose the correct locking amplifiers. And here, in order to make this choice, we need to look at different ingredients, different parameters. The first thing, of course, is the signal input bandwidth, which basically indicates which is the maximum frequency that the locking amplifier can handle at its input. Then we might want to look also at the measurement bandwidth that is related to the minimum and maximum time constant of the filters. We're going to take a bit of a deeper look here afterwards. And then also one might be interested in the input noise, indicating the physical noise that is added to the signal that I want to measure when I connect my signal to the locking amplifier, and the dynamic reserve that indicates the ability of the instrument to measure a signal from a certain noise floor. With Zurich Instruments locking amplifiers, there is much more than a standard locking amplifiers. Our instruments come with integrated toolset for real-time time and frequency domain analysis, for example, with an embedded oscilloscope or a frequency sweeper or a spectrum analyzers. Then with multiple modulators, one can achieve the modulation at multiple frequencies. We will see a couple of examples later, and of course also the Boxcar Averager functionality. Here on the right-hand side, there are fleet of Zurich Instruments locking amplifier. I would like to give a special mention to the new addition to our portfolio. As Magda already mentioned before, we have now the GHFLI and the SHFLI that extend the frequency range of our instruments up to the microwave, up to 8.5 gigahertz. Another important thing is that all Zurich Instruments locking amplifiers work in the digital world. So they analyze signals with digital signal processing technique, making it possible to demodulate at multiple frequencies without signal losses, for example, and to have smooth transmission of the signal within the instrument itself. Okay, so now we have already kind of introduced locking amplifiers. Let's now understand what is their working principle. How do they make a measurement? So the idea here is that we have our signal that is buried below the noise, as depicted here. And then we have modulation reference signal that come from, for example, our modulation in the experiments. That can be the signal coming from the chopper. Then we multiply this signals together, and this operation is basically the effect of shifting our measurement, our signal to around f mode. Then one runs signal through a low-pass filter, where this low-pass filter is basically a series of RC cascaded filters, one after the other, and then one in this way can obtain the amplitude and the phase of the signal with respect to the reference that we provided to the locking amplifier. Overall, so the transfer function of the instrument can be thought as a bandpass filter, the same one as the bandpass filter, with an arbitrarily chosen center frequency and bandwidth. So, to summarize, we need to have three ingredients in order to perform a proper locking measurements. We need to have the modulation frequency, f mod, again coming, for example, by the modulation in our experiment. Then we need to set the filter bandwidth, which basically indicates how many frequency components are allowed to go through the filter instrument, and then the filter order, which tells how steep the filter function looks like. About these two last points, we're going to explore them in more details in the next slides. Now, I would like to jump to the first application examples of today, where we look now at the fluorescent analysis at multiple wavelengths. Here, the authors of this work had 4 lasers at different wavelengths, and all of them modulated at different frequencies. They combined these lasers and shone them onto a microfluidic microfluidic chip, where some micro droplets were running through the channel. And these micro droplets were basically done with a different concentration of a specific fluorescent dye. Then the signal, the fluorescent signal emitted by the droplets would be captured and sent by a photomultiplier, measured by a photomultiplier, whose output would be then sent to the locking amplifier, which in this case was our HF2LI 50 MHz locking amplifiers, of course, together with the reference of the modulation frequencies of the beam. And the results are indeed pretty exciting because, yeah, thanks to the modulation at multiple frequencies, the droplets could be uniquely identified as we're running through the channel, as is shown here in this graph, where each fluorescent signal basically depends on the concentration of a specific dye within the droplet. In this way, the droplets could be mapped live in the frequency space, in the fluorescent space, according to their fluorescent fingerprint. So according to the fluorescent signal, which was given by the specific concentration of a fluorescent dye. So this is a quite powerful example of how much more information one can gain if can demodulate multiple frequencies simultaneously. Now, here you can see some very sharp and well-defined peaks, but how can we achieve this practically with our locking amplifier? Well, we have to play around with some instrument settings. So the first thing that we're gonna look at is the filter bandwidth. That basically indicates, that basically gives us the measurement bandwidth. The measurement bandwidth meaning how many frequency components are allowed to go through the filter. The bandwidth of the filter is proportional to the time constant of the filter, and since these are digital RC filters, basically given by the resistance and the capacitance of the filter themselves. Here we have the plot of the time domain response and the frequency response of the filters. As we can see, as we increase the time constant, basically we decrease the bandwidth of our filter. Generally, as a rule of thumb, the measurement bandwidth should be as narrow as possible in order to reject as much noise as possible, but at the same time should be large enough to support all signal components. To understand better what I mean here, I've plotted here a signal with 3 different filter settings to show you what is the actual effect on the measurement. So we have here the first on the left-hand side, we have a filter bandwidth which is quite large, and where we can see, yes, the peaks, but we can also see that there's still quite a lot of noise overlapped with the peaks. If we jump to the right-hand side, we have that now much narrower filter bandwidth, where we can see that, yes, the noise is suppressed, but at the same time, also the intensity of the peak is reduced, and also they're broadening, they are quite broadened. The peaks are smeared out. Therefore, meaning that probably the frequency that the bandwidth that we've chosen is a bit too narrow. In the middle, we have the best case for this specific example, where the filter bandwidth was chosen so that yes, the noise was rejected, but also the signal to noise ratio, so the amplitude of the peak would be preserved. Second parameter we can use to optimize our measurements is the filter order. The filter order basically means simply how many filters of the same type, identical filters, are cascaded one after the other. And as you can see here from the frequency response of a filter with a certain time constant but with high order, you see that the function of the filter steepens out as looking much more as an ideal brick wall filter. The trade-off of this is that the step response is somewhat maximized, so it's getting longer as we increase the filter order. So again, as a rule of thumb, the filter order should be generally kept as low as possible, so to minimize the step response, to make sure that our signal gets to the new value as fast as possible. But at the same time, should also ensure that all the noise components in our signal are correctly suppressed. Again, to better understand what I mean with this, I have here a graph and examples with two peaks now that were filtered with the filter order of 1, where we can see that there is a sort of a ringing, overlapped with the signal that we want to measure. And this is basically given by a spurious component that is interfering. So the spurious component that is really close in frequency to our the frequency components of our signals, and that is interfering with it. On the right-hand side, by increasing the filter order up to 6, so 6 identical filters, one after the other, you can see that the signal is the peaks looks much better, and this ringing component is suppressed. I would like now to shift the focus on a big family of techniques that go under the name of pump-probe-based spectroscopy. This family of techniques encompasses many different variations, and it's become quite popular in many labs, in many optics and photonics lab nowadays. In a nutshell, basically we have generally a pulse laser that is split off into two branches: a pump branch, which is modulated at a certain frequency, and then run through a delay line, and then recombined with collinearly, or also not collinearly, depending on the geometry of the experiment, with a probe pulse. Now, this pump pulse impinges on the sample, inducing some photochemical process, for example, that is then read out by the delayed probe pulse. By varying basically the delay between the pump and the probe, one can reconstruct the dynamic of the signal in a time-resolved manner. Of course, the signal from the probe pulses is then needs to be run through a lock-in amplifier or a Boxcar Averaging to be properly measured. Generally, pump probe schemes, we have that the pump branch is modulated maybe half the frequency of the repetition rate of the laser, meaning that for the probe pulses, we have one probe pulse that carries the information, and the other one that is doesn't carry information, that can be maybe used to normalize the intensity of our experiment. What I want to mention is that one of the reasons why pump probe spectroscopy has become such a powerful and also popular technique is that the time resolution of this experiment is basically only limited by the pulse width in time of our laser pulses. That is why, with very commonly used nowadays femtosecond pulses, but also attosecond pulses, one can study extremely fast dynamics of certain samples. So as I mentioned before, there are countless variations of this technique. Here I've brought you a couple of examples. We have a more classic two-color pump probe, where one uses a visible pump to induce photochemical process, which are then probed by a near-infrared laser pulse. Then we have a terahertz time domain spectroscopy, where essentially a pump probe scheme is used to electro-optic sampling to measure the transient, to measure the shape of terahertz pulses, but also in nonlinear microscopy, so for imaging application. Now, I would like, speaking about imaging application, I would like to show you a reworked version of a more classic pump probe microscope, where we use the capability of our instruments to demodulate at multiple frequencies. So here we have a setup which is very similar to the one we've seen before, where we have a laser which is split into branches, modulated, the pump is modulated at a certain frequency, then combined with the probe, and then basically the two beams are specially scanned, okay, in order to generate an image of a certain sample. In this configuration, then the probe, okay, as basically a signal component, so we show a signal components that at the modulation frequency of the pump. And now what we can think of doing is basically doubling this very same setup by adding second pump beam, a second pump beam at a different wavelength, and modulated at a different frequency. Now, we basically then run the same thing, scanner, and then onto the sample. And now the probe beam basically will not only have a signal component at the modulation frequency 1, but also at the modulation frequency 2. And with Zurich Instruments lock-in amplifier, you are able to demodulate this signal simultaneously at 2 different frequencies. Now, before elaborating a bit more on this, I would like to first show you sort of a raw image taken both by a lock-in amplifier and a digitizer. So on the left-hand side here, we have the signal that is directly sent without modulation after measuring to a digitizer, so directly digitized and plotted. Whereas on the right-hand side, we have the same measurement with the same measurement time. I won't stress this, so these two measurements are comparable. Instead, that is been analyzed by a lock-in amplifier. Here we're looking at some plastic beads, imaging of some plastic beads. I think it's quite clear, the self-explanatory, the fact that here on the left-hand side, where no modulation was applied, the signal was, you can barely recognize the beads, and the signal are then basically buried below the noise. On the right-hand side, with the lock-in amplifier, we see that we have sharp and well-defined beads that with a very extremely low noise floor. Now, you might have seen that some beads here are missing, and this is not because the lock-in amplifier has lost some information on the way, but rather the opposite. Indeed, if we tune now the two laser beams that we've seen before at 2 different frequencies, one matching the resonant frequency of, for example, PMMA beads, and on the other matching the frequency of polystyrene beads, we can measure these two contributions from these 2 different samples simultaneously. So these 2 images come from exactly the same measurement. And you can clearly see that indeed if you take a cut maybe along this line, you can see that the polystyrene beads sit exactly where the holes on the PMMA beads are on the left-hand side. So again, this is thanks to the powerful demodulation at multiple frequencies over the same signal. Now we have seen already a couple of examples about lock-in amplifiers. Let's move on to the second thing that we're gonna look at, the Boxcar averaging technique. As we've seen before how the principle of operation of a lock-in amplifier is, let's now understand what is the one of a Boxcar averager, and it actually is quite similar. The idea is that now, instead of multiplying our signal with the sinusoidal reference, we multiply our signal with the square wave, as depicted here, with arbitrarily short or long, basically, duty cycle. Then the signal is integrated within the Boxcar window, and basically the task of the low-pass filtering is performed by a moving average filter. And with moving average, I basically simply means that we are taking a certain number of Boxcar window and then just average together. To even understand better what this means, let's now have a look at an exemplary signal, at the short duty cycle signal, as for example here shown in on the left-hand side. Here, the plot on the left, we have a signal which is extremely short duty cycle. This could, for example, come from an ultra-fast experiment from our photodetector. And we see that the signal is really short. The information of the signal is confined really short in the time domain. At the same time, if we take the Fourier transform of this very same signal, we see that in the frequency domain, the information is distributed among many different harmonics, many different frequency components. So if we now demodulate the signal, for example, with the lock-in amplifier, we will basically catch only a single harmonic of this signal. If we now instead start to use Boxcar averaging technique, and we start to basically reduce the window of our Boxcar averager so that we are capturing more frequency components as in the frequency domain, we see that we are indeed covering much more of the signal than we would do with the lock-in amplifier. And basically, the amount of the number of frequency components that we are able to capture is inversely proportional to the duration of the window in the time domain, to the duty cycle of our wave. So I think it's clear here that when one has a very short duty cycle signal, Boxcar averaging indeed helps to acquire larger signal-to-noise ratios, because the signal is distributed in more harmonics. However, it's also needs to say that in the case of longer duty cycle signals, for example, that look more like sinusoidals, this kind of approach will not be so beneficial, because instead of capturing signal that would increase our signal-to-noise ratio, we would instead capture only noise, since the signal would not be so extended into the frequency domain. I mentioned also to the filter function, to the difference between the filter function of the lock-in amplifier and the Boxcar Averager. So as we've seen, the lock-in amplifier filter function is exponential type of settling. It needs an exponential time to settle instead. And basically, the settling time depends on the filter bandwidth and on the filter order. For the Boxcar Averager, instead, we have that the signal setting is linear, this red line here, and its settling only depends on how many Boxcar Averagers windows we are averaging to generate the new value. And also, there is no correlation, unlike lock amplifiers, with previous data points. A very technique that usually benefits a lot from the Boxcar Averagers, which I also worked with during my research years, is terahertz time domain spectroscopy. And this is because generally, still nowadays, to generate high energy terahertz pulses, we need high energy visible or infrared laser pulses that can be basically generated by amplified laser system that basically run at very low repetition rate, giving off a very short duty cycle signal generally. The experiment looks like this. We have an ultra-fast laser that is basically modulated, split into two branches, so similar to a probe. One branch is used to generate the terahertz pulses in a linear crystal, and the other branch is used to detect the very same pulses by means of the technique called electro-optic sampling, which is still done in another nonlinear crystal. So again, since generally this signal from terahertz time domain spectroscopy are quite low duty cycles, Boxcar averaging technique is generally a very beneficial technique to use to increase the signal quality. Another example, and the last example for today's talk, also regarding stimulated Raman scattering microscopy. This work is very interesting because the authors here actually compared exactly the quality of a measurement with the lock-in amplifier and the Boxcar Averager for their setup, of course. Here they had 40 megahertz fiber laser, which was split into two branches. One of the pump branch was modulated half repetition rate of the laser, so 20 megahertz. And then we combined, and the sample was scanned, and then the signal was acquired and measured both with the lock-in amplifier and with the Boxcar Averager. Here on the right-hand side, you have the comparison of the two measurements with the lock-in amplifier and Boxcar Averager, so that they would achieve the same signal-to-noise ratio. And they would compare how much time would then take for both techniques to achieve this specific signal-to-noise ratio. And as it's shown here, in this case, we have that the lock-in amplifier would take more than double the time of a Boxcar Averager technique to achieve the same quality. And this is, of course, not only beneficial because one reduces the measurement time by half, but also because if one is dealing, for example, with biological samples, there is also reduced probability of photo damage of such samples if one decreases the measurement time and the irradiance on the sample itself. Okay, so this leads me to the conclusion of the talk. So what we have learned today, I hope I've shown you that lock-in amplifier are versatile instruments that can be used in very different scenarios, and very different optical experiment. We've seen that a very powerful tool of lock-in amplifiers is to demodulate the signal at multiple frequencies, thereby increasing the information content and the signal quality as well of a specific experiment. This we have seen with the examples of multi-fluorescence analysis and double pump microscopy. Then we've looked at the Boxcar averaging technique, and we've seen how and when this technique is beneficial. That is when we have signals that are very short duty cycles, where the frequency extension in the signal is along multiple frequency components. And we've seen this pump probe techniques with the terahertz and domain spectroscopy and SRS microscopy. Right, so this leads me to the end of the talk. Thanks very much for your attention, and back to Magda now.
Gustavo, thank you very much. It was a great talk. I hope you also enjoyed it as much as I did. And now, while we're waiting for Gustavo to join us, we're going to start the Q&A section. We got a lot of interesting questions from you, so thank you very much for your contribution. You can still use the Q&A tab to ask anything you would like to learn more about the lock-in amplifiers and Boxcar averages from Gustavo. So let's start. Yeah, it's hard to choose, to be honest. Okay, let's start with a question from Michael. Could you elaborate a bit more on the optimum selection of filter order with lock-in amplifiers?
Yes, sure. So as I have explained also during the talk, so the filter order indicates how many filters of the same type are cascaded one after the other. Generally, one would try to use a high filter order when there is, for example, a specific spurious component, noise component, that is very close in frequency to the frequency of our signal. The trade-off of this is, of course, that the step response of the filter is somewhat longer, and therefore, for example, might be a problem this if the system is within a feedback loop, because we know that we need to have no phase delays if the systems are in feedback loops. But in general, so as I mentioned, one should try to keep the filter order as low as possible, but should also not be scared of using a high filter order in case the measurement needs it.
And a follow-up question: so how do you optimize the filter and the bandwidth, the filter bandwidth and the order for the same measurement?
So depending on the measurement itself, you first have a look at your signal and you try to understand which kind of maybe noise there is in your signal, and then you can start maybe with the larger bandwidth first and with the smaller filter order, and then try to narrow down the bandwidth and increase the order until you see that the signal quality is what you need and the signal is clear and not noisy. So it's of course hard to to generalize, but everything depends on a specific experiment. But I would probably start with the larger filter order and then narrow it down until the noise is suppressed.
Yeah, and we can also add that it's very easily done in our Lab 1 software.
Yeah, our software is really intuitive. We just can easily choose the bandwidth and the order of the filter with just one click, also not only on the user interface, but also with the APIs. So this is really smooth and user-friendly.
Yeah, operation.
Yes.
All right, now let's move on to the modulations at multiple frequencies. How many signals can you demodulate simultaneously with your lock-in amplifier?
Okay, so yeah, good question. So of course, how many demodulation in parallel can achieve depends on the amount of demodulators that a certain instrument has. And this is instrument dependent. So, for example, with the multi-frequency option installed in our instruments, we have that MFLI has 4 demodulators, HF2LI comes with 6 demodulators, and UHFLI, SHFLI, and GHFLI have 8 demodulators, which in principle can be chosen to at arbitrary frequencies, all of them. One important note here is that since as I mentioned, our local amplifiers work in the digital world, this demodulation in multiple channels does not come as a cost, for example, of signal losses, which would be the case with if one had to split the signal with the analog clocking amplifier. So yeah, this is a really powerful tool nowadays, thanks to digital signal processing techniques that our instruments use.
Yeah. We have a question from Amalia. Is it a problem when the ratio of beam to opening is small and the modulation as a square wave function?
No, I don't think this is a problem. I mean, one should try to, so if one wants to have a square wave modulation, one should try to have a beam that is as small as possible. But yeah, it also, again, this depends how sensitive your system is. It's hard to give a general answer here. But yeah, one should try to make sure that the beam size makes sure that the modulation function is what we want to achieve.
Yeah, you were showing a lot of practical examples, so I think that's why we also get questions that are very practical oriented.
That's great.
We have a question from Shaji. By locking the frequency, often we see that the signal is shaking and it's kind of difficult to lock the exact desired frequency. How can we improve this?
So when one provides an external reference to our lock-in amplifier, this reference is internally locked with one of our internal oscillators with a phase-locked loop. So generally, the amplitude of the signal is not relevant because, again, our signal is multiplied with the reference that is unity, as an amplitude of unity, which comes from an internal oscillator. What one needs to make sure is that the frequency of the reference is correct and there is no jitter. Maybe there is no frequency jitter, so that the frequency can be correctly identified by the phase lock loop, so that it's well defined. But generally, for example, the amplitude is not generally relevant for the reference signal.
All right. We're going to mix this up a little bit. Now we're going to jump to Boxcar Averagers, which you were also talked about. Tell us if our instruments, tell the audience, if our instruments have multiple Boxcar Averagers, and with which instruments we actually provide this option.
So yeah, the instruments that the option of the Boxcar Averaging is the UHFLI. And also in the future, we're going to be the SHFLI and GHFLI. The instruments come with 2 independent Boxcar Averager units that can act on 2 independent frequencies. Another interesting feature of our Boxcar Averagers is that they also come with the baseline suppression
going
window.
To ask that as well.
Yeah, exactly. So basically, one has 2 windows that can set. So one is the measurement window, and the other is the baseline suppression. That can be useful in different scenarios. For example, it can be useful to remove some slowly varying signal that is much longer than the shot-to-shot fluctuations. Or, for example, can also be used in pump-probe-based spectroscopies where one can directly make the difference between 2 consecutive pulses to calculate directly the induced transmission signal that we want to measure. And one last thing I would like to mention is that our instruments also have an arithmetic unit. And for example, UHFLI, all instruments, I think they have an arithmetic unit. And in this case, for example, with the 2 Boxcar windows, one could also directly do the ratio between 2 windows in order to maybe normalize certain signals, depending on the needs, of course.
Let's stay in the Boxcar subject. Tim has a question about how to correctly set the width of the Boxcar window to have the best signal-to-noise ratio. Is there any optimum width?
This is a very interesting and good question. So it turns out that, for example, if one has a Gaussian-shaped signal, the best signal-to-noise ratio is given when the window is not covering the full pulse, but about 90% of the pulse. This is, of course, a theoretical case, and the signal coming from a real experiment maybe it's not Gaussian, it's not the power of the signal is not evenly distributed across the pulse. And that is why one needs to optimize a bit, depending on the specific experiment, the Boxcar window width. For this, actually, we have a very interesting tool with our instruments, that is the sweeper, that basically allows you to sweep the width of the Boxcar averaging window and also the starting point, and plot then your signal to see where, at which width or which starting point, the signal-to-noise ratio peaks. So I think this is really powerful when one doesn't have still a lot of information and one needs to have a good starting point.
And this is all available with basically 1 or 2 clicks from our software.
2 click, you set the start and stop of the window that you want to try to optimize, and then that's it. You run it, and then you have your plot very fast.
Perfect. Sounds very simple. All right, now let's move on to more questions about pump probe experiments. When we do this type of experiment, there's a question from Hong Sing. The amplitude always is a positive number. How do you offset or normalize signal to get the positive and negative number, which means delta A over A?
So generally a lock-in amplifier, for example, gives you in output the delta I signal, and in order to normalize the signal, you need to basically measure by means of other way, basically the probe pulse in this case. Mm-hmm. So for that you would provide with that number, then you could calculate the delta I over I. If you do it, for example, as I mentioned before with the Boxcar averager, one could do it simultaneously, directly using one Boxcar averager for calculate the delta I, and the other to calculate the I, and then normalize it by doing the ratio with the arithmetic units of our instruments. So depending which technique you're using, you might need to resort to different ways of doing this.
Great. Another question, more fundamental about lock-ins, I would say. We normally get X and Y outputs from the lock-in, but there is no easy way to get R and theta directly from the lock-in. Is there a way to measure R and theta directly rather than X and Y?
So our lock-in amplifiers measure X and Y. Then, of course, one would need to calculate the R by doing a trigonometric, like the square root of X square plus Y square. But our instruments can provide in output, for example, with auxiliary output, directly the R, so the amplitude, the R of the signal, and also, of course, the measurement of the phase. So this is possible with our lock-in amplifiers.
And they can be nicely and directly plotted.
Can be plotted, can be also routed out from the instrument in case one needs the signal to be interfaced with other instruments in your setup. So this is extremely flexible. Depending on your needs, we have something that for sure works for your experiment.
Yeah. Let's move on to the new topic. Is the reference frequency the same as the frequency of the signal of interest? If not, what is the frequency deviation? That's more general.
So, I mean, the modulation frequency or the reference frequency needs to be the frequency at which your signal appears. So, as for example, if you have a pump probe experiment, you need the signal that you need to measure, that you want to measure, is basically the probe that you're measuring with the photodiode as a component, as a frequency component at the signal, at the modulation frequency that you're modulating your pump. So generally there is no, depending on what kind of modulation, the reference you're using, there shouldn't be any specific deviation. So the frequency of your signal is given univocally given by the modulation technique and the modulation that you're using in your experiment.
And we have a follow-up question on that. What is the limitation on the internal manual frequency modulation on HF2LI and UHF-LI?
So there is the limit, for example, so the instruments, the HF2LI, let's start with HF2LI, have a maximum input bandwidth, which is the maximum frequency of the reference that you can provide to the instruments. This could be both internally, with the internal oscillators, but also from external, which is 50 megahertz. So every frequency below that, our HF2LI would be able to handle and measure. For the UHF-LI, we have that the frequency is up to 600 megahertz. And regarding the frequency resolution, both instruments can provide, can measure down to DC first, and can provide the frequency resolution of around in the microhertz range, so extremely high frequency resolution. So the only limitation, I would say, is what is the modulation frequency of your signal. If your signal is higher than 50 megahertz, then you might want
to switch to
6 to UHF. Exactly.
Yes. There is a new topic, more on implementation, and what is this sampling rate of the lock-in amplifier? Maybe you can explain and the mechanism, the idea.
Of course. So when one wants to reconstruct a signal in the frequency domain, one needs to basically stick to the rules of the Nyquist theorem, which basically says that you need to sample a certain signal at double the frequency maximum frequency that you can resolve. So for example, let's take the example of the UHF-LI. Our maximum frequency is 600 megahertz. So it means that the minimum sampling rate that our instruments should have is double this, so it will be 1.2 gigahertz. Now, of course, our instruments there is a safety margin on this. That's why the UHF-LI, for example, has a 1.8 gigahertz sampling rate, giving enough oversampling to make sure that the signals are characterized correctly. So the Nyquist theorem, the Nyquist limit, is what one needs to take into account when talking about sampling rate and maximum frequency of a certain instrument.
I have to mention, thank you for the answer, for the explanation. I have to mention that we are slowly coming towards the end of the webinar, so I can maybe ask one or two questions. Maybe let's try to give a little bit shorter answers. As I mentioned before, we are going to prepare more elaborate answers for you and publish them, but in the interest of time. Question from Peter. The filters that you mentioned in the presentations are digital or analog?
Everything,
just to clarify.
Everything in our instrument is digital. So anything parameter you would change is a digital parameter. So there is no analog. Of course, the only analog thing is the analog to digital conversion that happens when you plug your signal into the instrument. But everything, all the rest, is digital.
And as a last question, I picked one that could serve as a general advice from you. So what would be your approach to finding the ideal bandwidth?
Yeah, as I mentioned before, the ideal bandwidth of the filter depends a lot on the experiment, so it needs some iteration to be done. But yeah, I would certainly try to have a large bandwidth at the beginning to make sure that I don't miss anything, any components of my signal, and then try to reduce it down to where I'm happy with the noise performance, but also making sure that my signal is characterized correctly and all the frequency components that make up my signal are correctly measured by the instrument.
Thank you, and we're going to leave you with that thought and general advice on improving your measurements. I really want to thank you, Gustavo, for a great talk and sharing your knowledge and experience. Thank you for the audience for spending the time with us and showering us with really excellent questions. We will get back to that with that to you in a publication. I also would like to thank the whole team that helped us today, Marjorie, Janos, and Claudius. We would like to stay connected to you, so don't hesitate to reach out to us. Write to info@zhinst.com, visit our website, follow us on our socials. We wish you a very nice evening. Thank you.
Thank you very much also from my side.